All right, thank you. Let's see, I want to open briefly with a comment that I made out in the front, which is we're going through a time of adversity right now. And, I'd be a fool not to at least acknowledge that. Uh, this is a strange time to be a student. And I want to call out people have graduated in adverse times before. In 1995, when I graduated from the West Bay Farm School, uh, there was an article in Physics Today about economic models for recent graduates, and we were compared to pollution. We're an unwanted byproduct of doing science, right? At that time, public funding was in almost as much jeopardy as it's in now, and jobs were scarce, and opportunity was hard to find. Now, there is some survivor bias in the people who are around today, but on the other hand, we survived as a field. And even in times of adversity, there is opportunity. So keep your nose high as you graduate, and remember to look around, scout for the opportunities. Don't dwell on the negatives because that's difficult. But look for the opportunities as you move forward. Anyway, I'm going to open. This is a talk about remote sensing. Why look at the sun anyway? Isn't it a big ball of gas? I got my start, West Bay Farm School, Stanford University, early 90s, working for a fellow named Art Walker. Art had, he pioneered a new technology for reflecting ultraviolet light, multi-layer mirrors. We use it all the time. You'll see lots of products of that technology in my talk later. I watched him talk to the material science department at the university for an hour about these wonderful materials that could reflect ultraviolet and let us look at the sun, who's a solar physicist. And at the end of the hour, the first question, somebody raised their hand and said this. So I want to remind us that we look at the sun because it's very interesting and there are important things to be done in it, right? It is a fascinating system. And so let's not get too bogged down in the technical details. I'm going to give you kind of an intuitive overview of the field, but I'm going to try and drill in and point out some of the phenomena you've heard about or read about or are studying that you can actually see in these images. But the sun is not just a big ball of gas. Betelgeuse is a big ball of gas. This is the first star other than the sun that we could actually resolve, is Betelgeuse. This was in the mid-90s using sub-pixel resolution with the Hubble Space Telescope using a scan. Andrea Dupree did this work. There's Betelgeuse, and there's the size of Earth's orbit and Jupiter's orbit. It's a really big star, and we can just barely resolve it. By contrast, at the same time, or a little bit later, we had TRACE, which was an EUV imaging telescope looking at the sun. And I guess the glyph showing the size of the Earth for comparison is not on this slide, but there's a lot going on here. We can resolve a great deal about this system. The sun is not just a big ball of gas. To be fair, Betelgeuse probably isn't either. But we can resolve these systems, and that means that there's a great deal to understand in much more detail and much more rigorously than can be accomplished with what I would call hand-wavy astronomy. And so talking about remote sensing in the context of the sun is talking about imaging and imaging spectroscopy, and that's what we're going to talk about now. We'll come back to images like this and talk about some of the details in it. So here's where we're going. I'm going to talk about the electromagnetic spectrum, just a brief refresher on the technologies we use to probe different parts of it and why they're helpful. What can you measure with photons anyway? And then I'll launch into a tour of the sun and how we measure it from the interior out to the solar wind. And I won't cover that entire topic, which is big. At least some of it goes to Tim Bastian, who will be talking about radio a little bit later on. But please forgive me, because this is a huge field, and this talk may seem a little rushed or disconnected in places because there's a lot to cover. And I want to make sure that we at least touch on a few points that will stick. At the end, I'll show you an example of signal separation. There's some object lessons and moral parables, if you will, interspersed throughout and we'll sum up at the end. So the electromagnetic spectrum, here it is. All of you are familiar with it. We have gamma rays on the short end, radio on the long end, DC off the right-hand side of the plot. All of these types of waves are useful for probing the environment around us. Most of them are quantized to a degree that, let's see, does this actually work? Oh, look at that. That's awesome. Most of them are quantized, right? They arrive in photons. From the infrared sort of on up, we see the photons. This end of the spectrum here that, Tim will be talking about, we don't really see the photons. We can use the classical approximation. The reason I've shown this particular spectrum is, why do we go to space? Well, we go to space for a number of reasons with our instruments for remote sensing. Some of them is to get above the atmosphere. The atmosphere is bright. Punch, my mission, is a visible light instrument. We could, in principle, work from the ground. There's a lot between us and space that gets in the way of the signal we want to measure. But some types of measurements, like ultraviolet or X-ray measurements, can't be done from the ground. The appropriate radiation just doesn't penetrate. So these are what we use these parts of the spectrum for. Gamma rays and X-rays are generated by non-thermal processes and solar flares. There are very hot plasmas on the sun that radiate and spectral lines in that part of the spectrum. X-rays, we see impulsive heating in active regions and that kind of thing. Actually, I want to go back to gamma rays for a second. I don't know if you know, the sun produces antimatter. In flares, you see the 511 kilovolt gamma ray line that comes from positron annihilation. And if you get out your favorite back of the envelope and work it out, an X-class flare might make as much as a kilogram of antimatter. That's pretty neat. Impulsive heating. In the ultraviolet, we can see coronal structure and dynamics. By looking at spectra in the ultraviolet, we can learn a lot about the different types of temperature that there are, and more about the density and physics that are going on there. In the far ultraviolet, we can see what we call the transition region, which I'll talk about a little bit. That's where the plasma undergoes the thermal catastrophe you may have heard about, where if you start with a plasma at 6,000 Kelvin and gradually apply more and more heat to it, it'll heat gradually until it reaches about something like 50 or 100,000 Kelvin, and then all of a sudden, bam, it's at 1,000,000. So where that transition takes place is sort of a thin nimbus between the chromosphere and the corona. That's the transition region. In visible light, we mostly see the photosphere. We see the chromosphere and some of the corona. We'll talk about that. We see prominences in the visible light and in the infrared. We can see the corona in the infrared. Neat stuff. And of course, in the radio, we can probe all of these things with just as much rigor and completely different techniques. Different parts of the spectrum are imaged in different ways or are focused in different ways. In the gamma rays and X-rays, we can't really reflect those photons very well. And so we use Fourier methods with grids that are at different angles and filter out photons by what direction they're coming from. And then we can sort that out. And a technique that ironically is reminiscent of what we have to do in the radio, where we also can't image. In between, we can reflect or refract rays and produce instruments that map particular incoming directions of ray, or if you prefer, particular phase relations of incoming beams to locations on a focal plane. That allows us to map the direction that light came in very precisely. And so a typical imaging instrument might have, instead of one detector like David was talking about, we might have 1,000,000 or 4,000,000 detectors that we have to mutually calibrate. But the reward for that is we get a much better overview of the system we're looking at. But what we're measuring with an imager or a spectral imager is direction, right? We're measuring the direction that rays arrived at the instrument. Now, this may seem kind of dumb because all of you folks have been through college and into graduate school and through it, but let's do this. Hold up your thumb, right? And squish my head, right? you can squish my head even though it's bigger than your thumb and your finger because they're closer, right, to your eye. Your fingers are closer to your eye. And so your eyes are measuring angle. And it's important to remember that because we often think of images of things of a certain size on the sun. But what we're really fundamentally measuring is angle and not size of features. And that comes into play with some of the coronal stuff. All right, let's look at the spectrum. This is just the visible part of the spectrum. I show this to undergrads and just point out that it's complicated. But there's a great deal to this complexity. You can see the familiar Fraunhofer lines here that you're probably well familiar with. Fraunhofer C, of course, is H alpha. That's the Balmer line that you learn about in chemistry. These are the particularly dark lines that are strongly absorbed by a cool layer above the solar photosphere, right? There's material at about 4,000 Kelvin above the 6,000 Kelvin photosphere. It absorbs light in these wavelengths. And so you see stuff missing. Sodium D doublet you may be familiar with from streetlights, right? Or if you do terrestrial work, you know that there's a sodium layer that glows. And the calcium H and K lines down in the near ultraviolet or deep indigo are particularly important because we can probe the chromosphere and transition region with them even from the ground. Let's look at the structure of some of these absorption lines. Okay, so a very strong one, I took two different spectra from two different papers and I scaled them to the same wavelength scale so you can sort of get a sense. At the top you have the actual, that's the calcium K line in the near ultraviolet. You can see it's very broad. It's a Fraunhofer line. Fraunhofer discovered it with kind of a cheesy, what today is like a 5-cent spectrograph that you can make with some cardboard and a CD. So it's very broad, very deep. And the structure of that spectral line actually lets you probe different depths in the atmosphere, right? The calcium interacts so strongly with the light that it's optically thick at different layers in the atmosphere. And as you work your way in wavelength, you're actually looking deeper and deeper higher and higher in the solar atmosphere. The core of that line, where the absorption is strongest, is actually self-reversed twice. You can see these little bumps here is actually an emission. There's calcium emission, and then above that, there's more absorption. So it's a really interesting line. Because you can study it from the ground, people have looked at that over a long period of time. And then the other section of the spectrum I wanted to show you is this is a little piece of red spectrum, 6173 angstroms. Some of you may recognize is the spectral line used by SDO-HMI. We'll touch on the measurement they make there. This has a very simple and narrow structure. That particular resonant line of iron does not strongly interact, just strongly enough to make an absorption line, but it doesn't have a lot of features to it. And that's important because an instrument like HMI wants to measure simple things like a Doppler shift or the Zeeman splitting without the complexity that you would see in something like the calcium line. So there's a great deal of, there's a large number of lines in the spectrum, and we can use many of them for very different types of observation. And that carries on not just across the visible, but up into the ultraviolet and down into the infrared. All right, so I'm going to talk a little bit about, I was going to talk about the physics of spectra and what we can measure, but I'm going to intersperse that into some of the images and things that you'll see. So this is what the sun looks like in visible light, or looked like in 2004, as seen from SOHO. You can see some sunspots going around. Otherwise, it's pretty boring. You're looking at the photosphere. It's the first optically thick layer of the sun in broadband. It's a few hundred kilometers thick, and it's at about 6,000 Kelvin, and it looks boring, right? There's not very many features to it on this large scale, aside from the sunspots. Those have been known since the 16th century. We look a little closer. So here we're not looking with something you might have in your closet in the form of binoculars. We're looking through think a 1 meter, no, 75 centimeter telescope at granulation. So this is an extreme close-up of the sun. Um, you're looking at convection cells on the surface of the photosphere. There's a little image of Texas there in the blue part of the image. That's a fiducial to give you a sense of what 1 megameter looks like on the sun. What you're seeing here is hot material coming up through the outer layers of the star, hitting the surface, cooling by radiation, giving off sunlight, and sinking. And so the time scale here, there's a clock which I've mostly obscured. Each of those convection cells rises, spreads, and shrinks in about 5 minutes. They're about a megameter across. So you're talking about flows of several kilometers per second. They're actually supersonic. So this is a highly energetic process. It looks very calming here. You could stare at granulation for a long time, but it's extremely energetic. And that buffeting produces all of the energy, most of the energy, that heats the solar corona, accelerates the solar wind. We don't know how that energy is released, but you're looking at the engine that drives the fact that we have space weather right there. These dark lanes in between are dark because they're cooled, so they're not radiating as much. And the contrast actually tells you a little bit about the stellar model. Different wave bands, of course, emphasize different things that you're looking at. If we look in a particular narrow blue section of the spectrum, this green, pseudo-green section up top, that's the same field of view. You can see the clock now. In the lanes, you'll see little bright spots moving around. Those are regions that are magnetized. The G-band is a particular forest of spectral lines that respond well to magnetism in the photosphere. So what you're seeing there is the sun's magnetic field. Remember, plasma is sort of like taffy, right? It's stretchy, but it's taffy that has magnetic field nailed to it. And so as this convection moves this stuff around, it's dragging and stretching magnetic field lines. But another way to say stretching magnetic field line is to say it's inducing electric currents. So you're seeing the solar dynamo in action, not the global dynamo, but a smaller local dynamo. And the interplay between those two systems is something that's still an object of study. It's not fully understood to what degree that local dynamo is independent of the global dynamo. And so anyway, but you can see it happening here. If we look in the calcium H line, that's one of that calcium doublet, H and K, that I was talking about, you can see an entirely different scene here. Whoop, it stopped playing. Do this. There. You can see much more contrast in magnetized regions, but moreover, you can see kind of a ripple effect, like the caustics at the bottom of a swimming pool. Those ripples are waves in the solar chromosphere. They're nonlinear. They're so intense that they're heating the material and causing it to glow brighter. You can actually see waves rippling through at strengths that are comparable to a kilowatt per square meter. That is an amazingly intense wave field. It carries enough energy to heat not just the corona, but the chromosphere, which is a much harder problem. You're seeing, if you stare at this long enough, you can convince yourself that you see shocks forming in those waves. So really interesting stuff. And it takes some processing and some doing, but you can in principle see this yourself through a telescope. And I have lots of labels here. Let's see. If we go in even closer, this is taken through a 1 meter telescope, the Swedish Vacuum Tower, quite some time ago now. You're looking in the G-band. You can see granules up top, right up here. And this was meant to be a movie, but actually I like it better as a still. You can see those G-band bright points, those magnetized regions. This region down here is a sunspot, of course. You're seeing the umbra and the penumbra. You can see the umbra, the dark part of the sunspot, is dark because it's highly magnetized. It's about a kilogauss field in there, 1 to 3 kilogauss. That's strong enough that the magnetic forces actually inhibit the lateral motions of convection. That prevents the granules from forming, which allows it to cool off. So that's underlying an active region. If you've seen EUV images of the corona, which you will in a moment, there's an active region above that. Magnetic field lines are coming straight out, and they're bending out like the fingers of a chrysanthemum or a spider mum, say. Uh, so the penumbra, that sort of semi-dark region that looks like the iris of an eye, is formed by field lines that are coming out almost horizontal. And they're allowing roll-type convection. So you're seeing rolls of convection there. Uh, Anyway, all of this is something you can see just through an ordinary filter. Of course, you need a vacuum tower 1-meter telescope to get that resolution. If we look at spectra, I talked about the 6173 line for HMI. This actually is from a different spectral line from SOHO MDI, because I had this movie around and it's just so beautiful. This is the sun, the solar photosphere as seen in Doppler shift. Right? So you Doppler shift the absorption line. The way MDI works and the way HMI works is you have a narrow band filter that's narrower than the spectral line. You take several images scanning through the spectral line, and you can get a measure of the spectrum at low resolution at every point in an entire image plane all at once. That allows you to do very precise relative quantitative analysis. In this case, we can see with our eyes on the focal plane the change in Doppler shift from the solar rotation. The right-hand scale is calibrated in meters per second. Blue is toward you, of course, and red is away from you. So there's the sun rotating, but what else is going on here? All kinds of crazy stuff. If we take away the solar rotation, just subtract that, what you see is a movie that should repeat but doesn't. Sorry about that. Let's see if we can make this happen again. There's the beach ball of doom. Okay, so what you're seeing here is near the edges of the sun, you see a static field. I'll run it one more time before we're done. You see a stationary pattern of blue and red. And in the core, oh, there we go, you see motions. Those motions are sound waves or infrasound in the sun. They have a period of about 5 minutes, which makes them 3 millihertz or so. And they are resonant in the body of the sun. So by studying the changing Doppler shift on the surface, you can actually use sound to probe the interior of the sun. So using photons to probe phonons, of course, you're in the classical phonon domain. If you think back to your junior year quantum class, we all had to do these perturbation problems where you know the eigenfunction of a particular Hamiltonian. You want to know the eigenvalues associated with a perturbed Hamiltonian, right? And you get like 3 or 4 different perturbations you're supposed to apply, and there's a matrix, and you turn the crank and you get out how the perturbed system behaves. Well, you can do the same thing on the sun as a whole. It's just that the matrix isn't 3 by 3, it's a million by million. So the MDI team pioneered this technique. Actually, members of the MDI team pioneered this technique. MDI really perfected it. And Gong and HMI are continuing and refining those techniques now. You can actually project those motions onto spherical harmonics and do perturbation analysis to probe the interior of the star. That is amazing, right? Because, I mean, Bertrand Russell used the interiors of stars as examples of things that don't really exist because you could never probe them directly. But now we can today, 100 years later. Absolutely wonderful. So this is a cutaway view of the sun from a few years ago now, showing the interior radiative zone rotating approximately like a solid body. The outer layers have this differential rotation and shear. There's a thing called a tachocline, which is a sharp boundary in between those layers. And then there are meridional flows on the outside. There's a whole science of that. But I want to call out just that you can do this, right? This is an amazing thing you can actually do with images. If you take 2 Dopplograms of a spectral line and subtract them, and the 2 Dopplograms happen to be through a right circular polarizer and a left circular polarizer, you're no longer measuring the Doppler shift, you're measuring the Zeeman splitting. Remember, so the Zeeman splitting is this coupling between the angular momentum of a photon and the angular momentum state of an atom. And so in the presence of a magnetic field, spectral lines split into a blue and a red component, and we can use that to measure the magnetic field, whoops, on the sun. Very cool. These are maps, magnetograms, showing qualitatively the magnetic field of the sun. They arrive calibrated initially in meters per second from MDI because it's a difference of 2 Dopplergrams. But they get calibrated in Gauss. You have to take them with a grain of salt because there's a lot of spectral stuff going on. People now work with HMI data, and understanding how to calibrate these things is itself an art. But to first order, if what you care about is that a north or a south pole and how's it evolving, you can just look and see. One thing I like to do is if you derotate this image, so this is the same data, but now reprojected to look as if you were hovering over a point on the sun, you can actually see the solar differential rotation happening. You can see that up near the pole, oh, come on. Can it happen? There's the beach ball of doom. All right, here we go. Up near the pole, there's slow rotation in one direction, down near the equator in the other direction. And that's the actual twisting of the sun, the differential rotation happening before your very eyes. You can also see the form when you, I'm not going to belabor that. There we go. You can see the form of eruption in a way that you can't if you just watch the active regions going across the surface. You can separate the secular motion, if you will, from how the magnetic field evolves as it emerges. There's a whole science there too, which we're going to press on from. All right, so we're about halfway done. Good. Go forward. Let's see, beach ball of doom again. There we go. Moving out from the sun, if we look at, here we're looking at the H alpha line. Look at the core of the H alpha line. On the surface of the sun, we see lots of interesting things. There's a bright surface down there. That's the limb of the sun. You can personally do this. This sequence was taken just a few days ago by George Kennedy and posted on Facebook, of all places. It was taken through a Meade telescope that you could just go by with a Lunt H alpha filter that you can also just go by. Now, George is good at post-processing to remove seeing effects and things like that, but this is something that you can just do. Like an amateur can do this for the fun of it. What you're seeing here is the limb of the sun with spicules, that's little bits of plasma that are shot up from the gaps between granules. They're shot up into the chromosphere. You can see a prominence down at the bottom here. That's this dark filament that absorbs material. Off the limb, the contrast is greatly enhanced out here, but you're seeing a filament as a prominence. When it's off the limb, it glows, and we call it a prominence, but it's really the same phenomenon. This is material that is, actually, I guess this is never mind. I want to talk about the prominence. This is a material that's suspended over the sun, many of its scale heights above the surface. So it's not just hydrostatically held there. It's suspended by dips in the magnetic field. The plasma is low beta, so the magnetic field is driving the show. And where there's a dip in a field line, the morphology of the field line is such that it can actually act as a cup or a container to hold material up. And that's what you're seeing right here. Some of that material is raining down the sidewalls. It looks like it's appearing out of nothing. That's coronal rain. And what's happening is condensation. You have this 1,000,000-degree plasma in the corona that's cooling off through that temperature catastrophe I talked about and dropping down to 50 or 100,000 Kelvin, where you can see it in H alpha. And then it's too cool to be there, and it's not suspended in a dip. It just falls right down the field in the 27 gravity field. Anyway, this is going on all the time. You can just see it with a telescope. But you can learn a great deal about the morphology of the magnetic field and what causes prominences and solar eruptions by analyzing the stability of these structures. Moving farther out, we can look at the same kinds of structures in the far ultraviolet. This is a movie taken with the viewfinder of the iris spectrograph. So a spectrograph disperses light, right, to spread it out into a spectrum. Then you get, if you just do that, you put like a grating in your telescope, you disperse the light, everything turns into rainbows and it's all confusing. So you have to put a delta function in there somewhere so that your integral doesn't integrate across the image and blur everything out. In this case, you've got a slit, which produces a spectrum where the slit is. And the slit is formed in two shiny pieces of metal that reflect the far ultraviolet. You can image everything except what you have a spectrum of. And so they're scanning the slit through this active region and studying it. Whoop, hopefully it'll start again. Maybe not. But where the slit is, you can get Doppler shifts, you can get temperatures, and all the other things you want to use to diagnose the plasma here in this active region. I'm going to keep moving. This is a still image taken with SOHO EIT, which again has been around for a long time. This is from 2000, which was also a time of solar maximum. And the corresponding magnetogram, just sort of showing how much magnetic field there is that's comparable to what we have now. I think right now there's 100 sunspots on the sun right now. And what happens in the ultraviolet over it. So what you're seeing here with the EIT and now with SDO is collisionally excited ultraviolet. This is far ultraviolet light. This is what I opened with. How do you reflect this and focus it? We have the technology to do that. It was developed in the 90s, and we use it now on SDO and many other instruments, or on AIA, many other instruments. But this light is made in the lower corona by collisional excitation of highly ionized species. What you're looking at here is iron 9 and 10. Actually, no, sorry, this is green, so it's iron 12, which is at about 2 million degrees Kelvin. It only emits, that species is only present at that temperature. And so you don't see the surface of the sun well. It looks dark there. It's dark because the photosphere doesn't glow at these wavelengths. You're seeing dark features on the surface. This smear right here is one. Those are coronal holes, right? You may have read about them, or you probably learned about them already. The material here is not gravitationally confined. It's so hot that the thermal speed is comparable to the escape speed. And so material just leaves, right? All of the corona that you see is quasi-confined magnetically. It's not fully confined, but it's confined enough to support the density that we see in the lower corona. And that's everywhere else in here. And the bright regions, of course, are above sunspots. Those are regions of additional heating from the magnetic field. In about 5 years, this is what the sun will look like. This is a solar minimum corona. There's not very much magnetic activity on the surface. And as a result, the corona itself becomes much fainter in the UV and much less structured. But the global structure becomes sort of more pronounced. You can see coronal holes over the poles of the sun because of the dipole magnetic field. But there's not very much going on in terms of the unstable magnetic fields that give rise to space weather at solar maximum. So, moving forward, looking at this in the high resolution, we have better movies now. This was made with TRACE, which is a late 90s EUV telescope, which has recently re-entered. I kept this because I wanted to show you some of the artifacts in the images. They're much more pronounced with TRACE data than they are with modern data, but they are important to see. In particular, TRACE was in low Earth orbit, so every time it passed over a pole, there was a storm of electrons that hit it. And you can see those in the form of some snow there as it goes around and around the Earth. You can also see that the electronics were not properly shielded, and so there's some wavy artifacts in there. That's radio frequency interference from the telescope's flight computer interfering with the detector. Enough of that. Let's talk about what we can see here. You're seeing a lot, right? This is a very evocative movie. You can see what looks like magnetic field lines all over the place. One of the things I like to point out early on is there's an eruption that happens here, and then over here, look at what happens to those loops, right? They jiggle, right? Those are plasma waves, right? In Marco's talk, you heard about the 3 modes of plasma waves, right? Those are Alfvén-like modes. They're not pure Alfvén modes because the density isn't uniform, but they're approximate Alfvén modes. They look like any other wave. What you're seeing here is a magnetic system that's weighted down by mass. The restoring force of the wave is the tension force in the magnetic field. You can reduce the energy in the field by reducing the length of a field line. So it acts like a tension on the field line. The mass term is the actual physical mass, not just the, like an electromagnetic wave has the magnetic field is the mass term. Here, there's actual ponderous mass that's slowing down the wave and causing this loop, which has a characteristic length, to resonate at a frequency, right? And we can measure the magnetic field in that loop by knowing how much mass is on it and seeing its resonant frequency. You can just see it right there. It's kind of neat. Down below here, you're seeing material that's not at 2 million degrees Kelvin. The surface of the sun is cooler and it emits most of this is iron 12. You're seeing oxygen emission down here, oxygen 5 and 6. That's the bright stuff on the surface. So you can fool yourself into thinking you're seeing only hot stuff, and what's all this hot stuff doing down here? That's not hot. It's chromospheric or transition region material. Up here, there's not very much material to interact with the light, and so this is all optically thin. You can look through it, and each pixel has an integral along a corresponding line of sight of the brightness. Okay, down here, of course, you're looking at the star itself, and so it's opaque. So you're seeing the surface. But what's all that dark stuff? It turns out really dense material is full of electrons, and electrons absorb the ultraviolet or scatter it out of the way. And so they look dark. So you can see here there's an interplay between optically thick and optically thin down in the chromosphere itself, which appears dark in this image. You can see there's kind of some shaking that's happening sort of at the characteristic 1 or 2 minute timescales, 3 minute timescales of the chromosphere. And then, of course, the corona is doing its thing up above. I want to call your attention to one other thing, which is scale height of this active region. You're all familiar. Who's familiar with scale height? Everybody knows what a scale height is. Okay, more or less. If you stack material hydrostatically, the density is proportional to the pressure. And so at a given temperature, you have a given exponential fall off in density with height. And so the scale height of that tells you the temperature of the stuff, if you know the molecular mass of it. The scale height of this material at this temperature should be about 0.14, 0.12, 0.14 solar radii. We're looking at collisionally excited material, or light. So the brightness varies as the square of the density, right? The number of collisions between like atoms depends on the square of how many there are. And so the effective scale height should be 0.07 or so solar radii. Okay, this thing is 1/3 of a solar radius tall. Why can you see the top and not the bottom, and the bottom at the same time? There should be about a factor of 1,000 difference in brightness between the top and the bottom, and there isn't. That's weird, right? But unless you stopped and thought deeply about this, you would never think. You just say, oh, of course, that's what the sun looks like. But it is weird that this is so many scale heights tall. And whoops, for a long time, we tried to explain that in terms of mysterious processes suspending plasma up. Right now, of course, we know that probably what's happening is we're not resolving this structure. The telescope can't tell you that it's getting smaller toward the base. It can only tell you it's getting fainter. So really, the base is intrinsically much brighter. It's just not resolved. And so it's attenuated by the fact that it's smaller than the pixels of the telescope, right? And that equalizes the scale height or reduces, it lengthens the scale height. This is a more typical movie that you might see now. SDO has many more bands and much more reliability and much more, it turns out, resolution and sensitivity than Trace had. So we built on the experience of Trace to make SDO. This is a combination of 3 channels of SDO data, 304, which is a helium-2 line that's mostly down at the base of the corona or in the top of the chromosphere, if you prefer. 193, which is that 2 million degree line, and 171, which is at about 1 million degrees. And so compositing the images in this way allows you to short circuit the process of temperature analysis, right? You're good at seeing the colors of things. And so you can just look at this and get a sense of what's hot and what's not on the surface or above the surface of the sun. So in particular, you can see that this prominence that erupts is not very hot, right? It comes out here, it's visible in the helium line. It looks red and not blue or green. Right? So this is cool material that's being flung out by the magnetic field. There's a lot to talk about here, but I do actually want to get you out of here on time. So we're going to keep moving. It turns out EUV emissions aren't just collisionally excited. We can see them really far out in the corona, right? So this is a highly processed campaign movie from the SUVI instrument that's used by NOAA as sort of a parallel to SDO. SDO was built as a science observatory. SUVI is built as an operational observatory to forecast space weather. They have similar capabilities. They're slightly different. But SUVI has in-flight spares, right? NOAA does everything by twos, so that there's always something. If one of them breaks, they've got another one. So one SUVI is in use at any given time, the other one is idle. And this fellow, Dan Seaton, who works with us at Southwest, was able to persuade them to use the backup SUVI for a campaign observation, which is this. So it normally points at the sun, and he pointed it off in 2 different directions over and over again and took very long exposures. And it turns out you can actually see ultraviolet emission way out here. Now, down in close to the sun, there's a lot of collisions. The collision time in the plasma is order of 2 to 30 seconds, depending on the feature. Out here, the collision time is hours to days, right? And by the time you get to about here, nothing ever hits anything ever again, right? That's just too sparse. So the plasma becomes acollisional. So what the heck are we seeing out here, right? We had no idea that there would be anything. Dan saw this stuff, and then we had to scratch our heads and figure out what it is. Well, if you look at the fall-off rate, which you can't see in this movie because it's been filtered out, just so that you can see everything. In here, the fall-off rate is consistent with that collisional excitation that goes like n squared. Farther out, it begins to drop off linearly with density. And you can see that the fall-off rate halves in slope. And what's going on out here is resonant scattering of light from farther down. There are just a few examples of that species. They're frozen in. They never hit anything else, right? So they're no longer coupled to the temperature of the local plasma. Just the ionization state is what it is. But it can resonantly scatter light that's coming from the sun as a whole. We can use that to probe this really interesting region, the middle corona, where all that quasi-confinement is taking place. Basically the nozzle that controls the solar wind. This is what the middle corona looks like almost to the naked eye. This was an eclipse image taken in white light. Electrons scatter light. So you can see electrons. Did anyone see the eclipse? Last eclipse? All right. So a few of us saw it. I like to point out that's what electrons look like, because the ions in the corona don't scatter light very well. The electrons scatter it very well. And so if you're seeing this white corona during an eclipse, you're seeing the electrons in the solar wind. Down at the base, you can see some prominences. That's the hydrogen line mixing with the Thomson scattered white light. We call this the K corona for continuerlich, which is German for continuum. It's lit by sunlight, and so it should have that complicated spectrum, and in particular, the Fraunhofer spectrum in it. But there are no absorption lines in it. Why is that? It's because electrons are very light and they're hot. And so they're moving very quickly. And the sun itself is Doppler shifted in the reference frame of the electron. And that smears out all the absorption lines. So this appears in continuum. But look at what we can see just from the morphology here, right? You can see the magnetic domains closing off and forming cusps here, and the solar wind starting to move out. You can see there's an eruption happening during this particular eclipse. This is the one 2 years ago in Australia, if I remember right. Heavily processed by Shadi-Habal and Druckmüller is the fellow's name, who sort of pioneered these composite images of eclipses. You can see some stars out here, really neat stuff. But what I want you to see is look at this part of the image and think about what's causing that. The lower corona looks like loops because beta is really low, right? It's following the magnetic field. Why is this radial? Beta is still really low. It's because of the solar wind. The solar wind is flowing out supersonically. And so there's an effective ram pressure that's much higher than the actual gas pressure. And so the effective ram beta is less than unity. So the ram pressure from the solar wind is driving the show here. That's why all this turns radial out here. You can actually see it happening, right, where those cusps are. So neat stuff. That's the transition from magnetically dominated corona to solar wind dominated corona out here. This band in here is what we now call the mid corona, and out here is the outer corona. Moving farther out, the outer corona is every bit as complicated and weird as the inner corona. This is a deep field campaign made with stereo. It is the deepest exposure campaign of the corona to date. And it just shows that there is a tremendous amount of structure in here, both in the form of transient stuff moving out in all directions all the time. That was so surprising to those of us who grew up looking at LASCO images. We called it a riotous torrent of material heading out. The data are actually consistent. They don't tell you that everything is this. They're consistent with there being no steady coronal flow at all. Right? There might not actually be a smooth outer corona of any kind. It might all be ejecta. Data don't tell us that that's the case, but they can't rule it out. And the fact that they can't rule it out is itself surprising. So moving out, if we go farther out, we can see the end of the corona right out here. There are two different sort of common definitions of the top of the corona. One is the Alfvén surface. You may have heard of that. That's where the flow speed exceeds the fast MHD mode speed. When it exceeds the Alfvén speed in the radial direction, that's where the plasma becomes causally disconnected from the sun. So if I move a little bit of plasma around in the corona, I can in principle affect the whole corona. In fact, you can see that when CMEs go out, the whole corona responds. If I shake some plasma way out here outside the Alfvén surface, it can't affect the corona because that signal can't propagate back into the star. Okay, that's one definition, and that surface happens somewhere around maybe here. Parker Solar Probe has flown through it a couple of times. It's a variable thing. We're studying it with punch. The other thing that you can see here, the other boundary, is a local boundary, not a global one. This is the beta equals 1 surface. Somewhere around here, plasma beta increases again. The reason for that is field lines are coming out radially, so the magnetic field drops off like r squared. So the magnetic pressure drops like r to the 4th. But the gas pressure is only dropping like r squared. So eventually the magnetic pressure crosses the gas pressure descending, and the gas starts to run the show. When that happens, these radial lines bust up, and you can see that the flow breaks up like the streamer from a squirt gun breaking apart. Anyway, you can see that happening with your eyes here. But again, you wouldn't call it out unless you looked with the eyes of understanding. So there's a great deal to these images. This is a CME coming out. I just wanted to show you this because there's a tremendous amount of structure in these things. And in fact, on my own computer, I can pause this right where I want to, but I can't here. I'm going to call it out. I'm going to say now, and I want you to look for a tower coming out of the sun. Now, that thing. That is the core, the twisted core of a CME. Right? That is a remnant coronal structure that's been expanding as it comes out, driving all this material before it. All this other stuff is bits of the corona that have been pushed out by the eruption. We can sort all that out here. We're hoping to do more of that with punch because we can image this in 3D. I've got to pick up the pace here. If we look even farther out, zoom out, we have to move to a different coordinate system. So we're going to move to conformal polar coordinates like this. All right. So now the limb of the sun looks like a vertical straight line. Okay. And we have 5 different instruments field of view going from the lower corona out to 90 degrees from the sun. This is using a mission called Stereo that flew some time ago and was a prototype for a lot of things that we're doing now, as well as sort of pioneering this type of measurement. In these coordinates, we can actually see a solar eruption forming down in the low corona. It's going to loop around again. You'll see it form right around here, coming out through the corona itself into the inner heliosphere, this field of view you just saw, and out into interplanetary space, washing over Venus and then the Earth. When it impacts the Earth, it had to sweep over 2 different spacecraft with in situ suites that measured it. The density gauge is being driven by those data, but there's a lot more to it. This was our first sort of event that Stereo caught that showed that, yes, indeed, we don't have to make inferences. We can track these events all the way from their origin in the atmosphere of a star until they impact our planet. So I like this movie because it shows what we do as a science community. This is heliophysics in a nutshell. Images aren't everything. The information that we get out of images is limited. And in particular, these white light images only show us a line integral of density. They don't really tell us anything else. I mentioned that ACE was in the way of this event, or 2 different spacecraft, WIND and ACE. And they sampled the event. And so we have tracks of in situ data, what I used to call confusograms, of the event. And they show all kinds of stuff. This is the wind speed. This is the density. This is the temperature of the plasma. Down here, we have the 3 components of the magnetic field, except it's in polar coordinates. So this is phi, theta, and the strength. I've color-coded this stuff according to type. And the type is in part determined by this, which is a spectrogram of non-thermal electrons. There's a really neat thing that we use that for, which is near the surface of the sun, there's reconnection going on all the time. And it's like shooting stuff out. Well, one of the things that happens is electrons go spiraling out. The reason the lower corona looks like it has field lines in it, remember, is there's the Lorentz force, motion field force on a charge. And so charges in general go in helices around the magnetic field lines. If you stand back far enough and squint, a helix looks just like a straight line or a curved line. And so electrons that happen to be going almost straight along the field that are launched out near the sun propagate all the way out the field lines, all the way out into interplanetary space. And so by looking at the pitch angle distribution, that's this 0 to 180 relative to the magnetic field, and we look at how many electrons are moving along the field or against the field, we can actually determine which end of our local field line is connected back to the sun. You can do that in situ. That's really neat. And so we can determine here, for example, right here, you can see there are places where there are two peaks, one at 0 and one at 180 degrees. Both ends of that field line just recently erupted from the sun, right? That's the sign of a loop coming out of the corona and washing over the instrument. That's really cool. And then, of course, there's some back and forth here. It goes up and down just because which direction was the field facing as that part of the material left the sun. But these places where there are two streams of electrons, one forward and one reverse, are places that we know were recently connected to the sun. And there hasn't been more than about an AU or two of integrated line along the field line before it washed over the spacecraft. So, neat stuff. Anyway, from the images, we can assemble a cartoon. And from the in situ data, we can color code the parts of the cartoon. We can understand exactly the correspondence between what hit us and what left the star. That is really neat. So merging in situ with image data is challenging, but it's also rewarding. It gives you a fuller understanding of the system. All right, Parker Solar Probe has been flying through the corona, sampling it in situ. It's also been imaging it in situ. How are we doing on time? Terrible. All right, I'm going to skip some later stuff, but take a moment to talk about what you can see in this movie, because it's not just pretty, right? It is pretty, but it's not just pretty. Watch this eruption that was caught by Solar Probe and look at, in particular, the edge of it. You can actually see plasma instabilities happening there. You can see the Kelvin-Helmholtz instability happening between two streams, right? So this is telling you about a great deal about what's happening in the plasma, even though you can't measure it directly, right? You can actually see features twisting around, forming vortices, and forming perturbations that grow with altitude, right? So that is turbulence forming in the vicinity of this eruption as seen from up close. There are other things that we can call out. You can see little plasmoids forming. You can see that is a central flux rope. Watch the core of this thing as it comes out. You can see some coiling and a helical structure as it goes by. All of these things aren't just image features. These are telling you stuff that people try to diagnose in the plasma. Nick is standing up, so I better finish. Oh, right on. All right, if you're not asleep yet, I'll try and get you there. You can see the stars moving by in the background. And then up front, you can actually begin to see, well, let's watch this go by again. You can see pileup happening, right? There's a pressure wave in front of that thing that gets brighter as it goes out. Now, some of that you have to be careful about because there's radial filtering happening. But also that is the bugs accumulating on the windshield of the CME as it comes out through the corona. All right, seen from near Earth, this is what a CME looks like, a halo CME. This is one that's coming right at us. If you're of a certain age, you remember a particular Star Trek episode that I love called The Balance of Terror about discovering the Romulans. And they have this new plasma weapon that just gets bigger in the view screen. And that's how you know it's aimed at you. That is, right. So that is what you're seeing here, right? That is a coronal mass ejection that left the corona aiming straight at us. And it's getting bigger. It goes all the way around the sun because of perspective effects. It's about 10 degrees wide relative to the sun itself, but it's coming straight at us. You're seeing this in the LASCO, the venerable LASCO coronagraph. It's been operating since 1995 on a 2-year mission. But because it's been around so long, that is what we know about the corona. The outer corona, this is what it looks like in the popular mind and the scientist's mind. The field of view here is about as big as the constellation Orion. This CME did not stop here. And in fact, this is where I get to advertise Punch. We saw that same CME propagate all the way out from the sun to the Earth. So these are early data from Punch, which has 4 separate spacecraft that look out in all directions around the Earth. They're in orbit. This is early data. We had not yet removed all the artifacts. That's why you can see that propeller motion going on as the spacecraft orbit. We've only suppressed the star field by about a factor of 30 here. So we're far from done. You can see CMEs leaving the sun and propagating across the solar system. This is the first time that this has been done from the Earth vantage point. So as this comes around again, you'll see this, let's see, we're on the 3rd, it'll go back to the 30th of May. You'll see that same CME coming straight at you. If you watch closely, you can actually see it go all the way to the edge of the field of view. Here it comes. Boom. Wham. It took about a day to go from the outer reaches of the LASCO field of view all the way out until impact with the Earth. So with Punch, right now we are learning how to clean up this star field. We have to co-align 4 different telescopes' output to better than a 30th of a pixel. We have to co-register them that well, and then we have to photometrically calibrate them to 1 part in 10 to the 4. Yeah. Aha, so the question is, if there's a CME that's coming at us, why are there no energetic particles? The answer is we filtered them out. So yes, and in fact, once the CME impacts, you'll see that there are more artifacts in the field of view. It just looks cruddier. And the reason for that is there's a lot more filtering going on. So the other thing to see is right after the halo CME, you can see another one leave the sun to the north. Here's the halo. Watch to the north, you'll see it go out. These things go out and cross the solar system. They don't end at the sun, right there. This goes all the way out. We lose sight of this one in this data set, right in the middle of Perseus, say. But of course, we ought to, in the final data, be able to get it much farther out. So this is the sun in context. There's a lot of other objects in the way. We kind of wish that there weren't any stars. That was sort of selfish. But this is the sun in context. It is a star among stars. And the things that are crossing our solar system are celestial objects that are dynamic and sweeping over us. So this is what we're hoping to study more with Punch. These are baby pictures of the spacecraft before they launched. They're about 1 meter long. That's a dude standing there for scale. This is how they're supposed to work with the fields of view overlapping. The spinning is much faster in the movie you just saw. That's a simulated CME in the background. Here we go. This is our first light image. I want to call this out. This is the zodiacal light. This is what our images really look like. They're basically star fields. I mean, the green markup is something we added later. We measure polarization. We measure polarization so that we can infer the 3-dimensional structure of what we're looking at. I'm not going to talk about that at great length, just mention that that's why we do it and that we can do it. Our coronagraph suffers from stray light, but we are reducing it. This is our proof of concept for how to tackle that. And we're just comparing it to LASCO C3. You can see that we see a lot of the same features in it. Pretty excited about that. I want to talk briefly, if I have time, about signal separation and why, this is something David talked about. There's an interplay between how hard you work at reducing the data and how much you trust the data. And so I just want to show you what goes into imaging these things far away from the sun. These are images from the widest heliospheric imager on board stereo. Some time ago, these data were collected in 2008. Stereo A was looking back toward the Earth from ahead of us in orbit. It has a CCD on board. That's a device that ejects electrons into a little storage reservoir whenever a photon hits the chip. Okay, if too many photons hit, they spill over, and they spill over in the direction of the readout wires. That's what these vertical bars are. So you're looking at Venus and the Earth, and these vertical bars are just spillover because those objects are so bright. You see constellations in the background. If you're astute, you'll recognize Pisces up here, right? There's boom, boom. And this stuff over here is not stray light. That is zodiacal light. also called the F corona or Fraunhofer corona. We talk about the K corona, and in an eclipse, you see the K corona, but farther away from the sun, about 3 or 4 solar radii away, the K corona becomes more faint than the F corona, the Fraunhofer corona, which preserves the Fraunhofer absorption spectrum, right? That light isn't scattered by electrons, it's scattered by dust, right? This is remnant dust, and it turns out there's a whole ecosystem of dust, which I could talk about for an hour, but won't. For now, just recognize that it's something that gets in the way of what we want to see. So we have to get rid of that stuff. And in a coronagraph, we have to do it. In LASCO, it's about 30 to 100 times brighter than the K corona. So we have to subtract that out. If we do that with these data, before we go, look at the brightness scale. This is in counts. These are 2-hour exposures. This is counts per second averaged over 2 hours. Okay, so 0 to 30. All right, so when we subtract the F corona, we can zoom in a little bit on the dynamic range. So now we're 0 to 1. That's why it looks like there's so many more stars. But there's a simple step here, which is take the entire data set, treat each pixel as a time series, and just subtract the minimum value, right? That gets rid of the steady part. Because the F corona is approximately circularly symmetric, it's sort of stable in the images, so you can get rid of it that way. You can start to see that there's something going on over here on the right. You can see halos around the planets now. That's scattering in the lenses of the optics from the bright planets. But there are too many stars in the way. So we can do the same trick. We resample to fix the stars, right? And now in this coordinate system, we can take the minimum value of each pixel again. We do that. Right here you can see there's 3 planets in this field of view. That's Uranus right there. You can see it jump at the end of the movie. Boom. If we subtract the minimum value of each star, we now get something like this. This goes 0 to 0.1. So we're a factor of 300 inside the original dynamic range. Now what's left over is statistical artifacts from the stars, changing the noise field, and a gradual north to south progression because we don't actually orbit in the plane of the ecliptic. We're slightly out of it. And so that dust cloud moves slightly in the field of view. What you're seeing is the residual motion that we didn't account for. So we can take each pixel and fit it with a cubic instead of constant value. And that gets you this. Now we're starting to cook with gas. You can sort of see that there's something going on here and crossing the field of view. This is about as far as we could get in 2011 until we recognized we could use the Fourier transform. You all know about the Fourier transform. You may not recognize it. If you have a time series that goes x and t, and you Fourier transform it, you get k and omega, and that data set looks just like a k omega diagram from your waves class. And so the Fourier transform of a time series isolates things by motion. But we can get rid of all the data that isn't moving the way we want. That's cool. So if we do that, this is all the things in that data set that are moving in the way that we expect the solar wind to. Now we can see the solar wind as a whole. There are some artifacts. You can see little bits of ringing from the Fourier transform and the reverse transform. So we get rid of that by processing the data in batches. We do multiple batches. The ring is there in each batch, and they all interfere destructively, and so then we just get the movie we want. This is the solar wind crossing the solar system. The artifacts that remain mostly are these stars that are showing up because the detector on this instrument is slightly nonlinear. Turns out it's nonlinear at the sort of 0.5% level, and that's enough that when a star moves across the pixel grid, it's the brightness of that star changes by up to about 0.5%, which sort of lets it poke through and make these telegraph effects. Let's see, there we go. And then the other thing is you can see this sort of looks like an old-timey movie, overcranked and undercranked. That's because there's a mechanical shutter on this instrument. And it's only good to about 1 part in 10 to the 3 for exposure time. And it turns out that's enough to screw this up. And then telegraph stars we talked about, well, 0.2%, not 0.5. All right, so what? We can do image and spectral analysis, and we can learn fundamental things about the plasma. I've been waving my hands a lot. I didn't show equations like Dave did, but I hope that you can drill down in your mind into the equations. I tried to point at particular phenomena that the equations describe, right? And we can actually be rigorous about how we interpret these images. We need both in situ and remote sensing. They're complementary. Remote sensing gives you not very much information about a lot of stuff all at once. And it turns out the morphology and the dynamics are important. Though I have another lecture I give that's an hour long about all the things that go wrong when you assume too much about images. If you trust your visual system too much, right, then you can misinterpret these things easily. In situ tells you everything you need to know about one place. And so the combination of them is really good. Imaging and spectral imaging give us information about the spectral dynamics. I mentioned the fraught with peril, use care. Think about what the experiment can actually tell you about the system. And that echoes in weird ways. I talked about the scale height of active regions in the EUV and how weird that is, right? But if you didn't stop to think about it, you might just accept, oh, that's how tall these things are, and I'm seeing all the features, right? But here's a really esoteric effect, resolution effects at the bottom of the scale range. It's affecting something that's as large as the entire field of view in those trace data. So you always want to think about what the experiment can really tell you and what it can't tell you when you're trying to draw inferences. So go forth, look at some data. Thank you. I think we may have, what, 5 minutes for questions? Oh, right on. Awesome.
Do you mind going back to the spectra of the non-thermal electron? I'm sorry, that went by too fast for me and I didn't quite understand.
Oh, at the very beginning, we were talking about gamma rays and non-thermal electrons?
No, the confusograms
Oh, here we go. Let's go
with the
back.
middle plot.
Oh, that. Oh, yes. Yes, yes, absolutely. This.
Yeah, yes.
So,
Yeah.
go ahead.
No, I guess, yeah, it wasn't clear to me how the pitch angle and the B field will tell you which way the electron. I missed
So,
it. I really did.
if you were to plot the electron flux versus pitch angle, right, you get some plot, a spectrum of that. Electrons can travel along the field pretty well. There's a certain number of times they go around the field on average before they leak out onto another field line. If they're coming along the field, they can actually get a long distance before that happens. For ones that are closely aligned to the field, either parallel or anti-parallel, that can be like 4 AU, right? And maybe 2 for ones that are an angle to it. So the presence or absence of that beam of electrons along the field line tells you what the other end of that field line is connected to, right? So if I were to walk there's a difference between streak lines and streamlines, right, in a time-dependent system. A streamline is what a line is connected to right now. A streak line is, if you allow the fluid to evolve, how would a test particle move? But the electrons are moving very fast compared to the solar wind itself. So they tell you information about the streamline, about the magnetic field line as it exists right now. And so if one end of that field line happens to be connected to Jupiter or Ganymede, and the other end to the sun, Ganymede isn't producing a lot of energetic electrons, but the sun is. And so you know which end is which, right? So when you see two beams, you know that a loop of magnetic field has just left the sun and swept over you. And that's actually there's an interesting canticle on that, which is people who study the sun in situ or study the solar wind in situ call that a closed field line. People who study the coronal magnetic field call that an open field line. And so people can argue about what's open and what's closed, right? In general, open has meant something that doesn't connect down where my instrument can see it, right? So somebody who studies the low corona will say any structure that passes through the top of the SDO field of view is an open structure. Well, that's not necessarily the case, right? Some of them close back down again. You can see those streamers go out, and there's a cusp, and there are loops that go out to almost 2 solar radii usually, right? And so something that's that tall might be closed to a person who studies the mid-corona. So we have to be careful about our nomenclature too, because we tend to get balkanized as subfields, right? And so sometimes we use the same word to mean different things.
I have one more question. Sorry. Sorry. Uh, and then when we talked about the Doppler shifts and things, if do you for non-Doppler shift images, do you need the spectral resolution to be really small, or can it be kind of
It depends.
broader
So
band?
those EUV images have lambda over delta lambda of like 100. And that's enough to allow you to image a cluster of lines. And if there's 1 or 2 bright lines in it, then we say it's a that species image.
Right.
But really, and I call out the oxygen for that reason, you're seeing a lot of spectral lines in one narrow passband. And so you have to sort of sort them out by the morphology.
Thank you.
So for the EUV images, we see that they are affected by degradation. Specifically, 3 or 4 is very strongly affected by degradation. So is there any solution from the instrument side, or do we rely on the post-processing of the data to get like the right data products?
So there's degradation, you mean the instrument decays over time?
Yeah.
Yeah. That's notoriously difficult to solve. And so once the instrument is up, you post-process. But the real answer is to lobby and get more funding to fly more instruments.
Thank you. I want to ask a question about I think it was the first part when you mentioned that we sometimes observe surface waves or waves on the surface of the sun.
Mhm.
I was just curious to compare it with, for example, earthquakes. I remember from like my basic knowledge about earthquakes, when earthquake happens, you see 2 fronts. So one is the surface waves that propagate, and the other front is the waves that propagated inside and then are reflected back to the surface. I'm just curious if you see some similar phenomenon on the surface of the sun.
Absolutely. So there are multiple wave modes that are present. P modes are the main ones that propagate through the solar interior. The S waves for an earthquake are shear waves, and they go slower than the pressure modes. So typically you'll get a strong earthquake, and then either the tail end of the shaking or maybe a subsequent bout of shaking is the shear modes that propagate more slowly through the earth. We do see there's something called the F mode, which is a gravity wave, very similar to what you see coming off the ridges here. If you ever look up and see a hot dog bun shaped cloud coming off the ridge on the Front Range, that's actual atmospheric gravity modes. We see gravity modes down in the radiative zone too, or we should, but nobody's detected them yet. Those are, the restoring force on those is buoyancy. And of course, in the convective zone, you're unstable against perturbations. And so there is no gravity mode there. Gravity modes do exist in the radiative zone, we think, though there's no direct evidence yet. But they're evanescent for something like 10 wavelengths coming up through the convective zone. And so they're very hard to detect on the surface.
Thank you.
I was just going to follow up since I do actually have some background in astroseismology. We do actually have evidence of gravity modes in larger stars or mixed modes in red giants.
Cool.
I have kind of a crazy question. Because you were mentioning the stars at first. I'm just wondering how many years is it gonna take for us to resolve those features in the stars, like the outer regions?
How many years will it take for us to resolve features on stars? I don't know. The diffraction limit from EUV is much smaller. The photons are smaller. So you could presumably image the coronae of stars with something the size of a dinner platter, a serving platter, in the EUV. But the tolerances and the pointing are just too difficult to overcome now. But I think in your lifetime, you'll probably see the coronas of other stars.
Oh, really?
Hi, Craig. Thank you for the great talk. I guess I have more of a generic question. We got a lot of lectures on like theory and now observation. So as an early researcher, let's say in observation, how much time should I spend understanding theory? And then how do I balance? Like it seems all of these go together. So it's just a
How do you balance? That is a really excellent question. I am a consummate generalist. I believe everybody should know a little bit about everything. In particular, what makes an effective scientist, somebody who can really tear up the turf, is somebody who knows enough to be dangerous in one of those fields and really understands deeply the other one. If you silo yourself too closely in either theory or simulation or measurement or instrument design, any one of those things, you run the risk of becoming disconnected from the big question, right? What we as scientists have to do is think about the big questions and connect those to the mundane, everyday, trivial things we have to do to get our work done, right? But you should know as you're turning a screw on your instrument or fixing a line of code in your model, how does that particular line of code connect through 3 or 4 layers of indirection back to the big question you're trying to answer? And you can't do that properly unless you have at least a little knowledge about everything. So you do need to reach out, try and really understand at least the basics of each subfield that touches on what you're doing.
I haven't spoken yet, but to their sort of take on that.
Please, please do. Or I could deliver you guys the lab. Does anyone want to weigh in on that?
Oh, there you go. Yeah, that's a really good question. I think I agree a lot with Craig's responses. I think I would say something very similar. The other thing I would add is that you build teams. No science happens with one person. That idea of the like lone scientist who sits in the basement and solves everything by themselves is a complete myth. And it's for the reason that you bring up. No one can be an expert in all these pieces. There's too many pieces at this point in scientific exploration. And so you build a team, right? So maybe you're the person who knows more about instruments. You should know a little bit about each, but maybe you're that person. Maybe your colleague that you work with knows more about the simulations. Maybe another knows more about the theory. And you really have to build teams is my answer to do that. And you have to build these close collaborations where your knowledge gets you some way into it. You kind of vaguely know what's going on, but then when you have a detailed question, you find the expert on it, and then you work together to flesh out the full problem.
Yeah, I don't disagree with anything that David said or that you said, Craig, that, these are vast domains and we have, limited suites of tools with which to explore. There's theoretical tools that lead to understanding. There are the observational tools in situ and remote sensing. There's modeling now, which has come to the fore over the past several decades. And now, of course, we're entering the era of AI. Certainly, I think many perspectives are needed to make sense of each of these domains, and so having teams is very important. When I started my career, 1, 2, 3 co-author papers were commonplace. Now you have very large teams and they're usually series of papers based around instruments or models or what have you. So sort of the nature of science is changing. It's too big for any one individual to grasp. And so the teaming is very important. I will watch with interest to see what the impact is as we sort of begin to leverage machine learning and AI based tools.
And I'll add from somebody who focused a lot on the data side and the data analysis, definitely don't hesitate to reach outside of our disciplines to statisticians, to computers engineers, to signal processing experts. I mean, Farzad and I have worked together for over 20 years, starting by reaching out to bring in statisticians and experts in a lot of fields like medical imaging and things like that, which we bring to solar imaging and whatnot. So I think that's really critical. Personally, and when we started this, I always felt like we physicists had this tendency to try to do it all ourselves, and learn it all ourselves, and it's impossible. And we're never going to get a PhD in those fields. Doesn't mean you shouldn't be competent and understand, but it's also a matter of learning to communicate. So the communication side of that is absolutely critical. Learning language, learning to be able to talk across disciplines to make those connections is really, really important.
More questions for either Craig or Dave. I'll open the up to our general Q&A.
Do you mind talking a little bit about how the coronagraph works? Is it necessary to do all coronagraphs have like a wavefront correction situation happening, or is that
So
specific to
how does a coronagraph work? The simplest answer is you block out the sun itself. The photosphere is too bright. The corona is between 10 to the minus 6 near the surface and 10 to the minus 14 or 15 times the radiance of the photosphere. So you got to block that out. Then the question is, how do you do that? I almost threw in an image here of the first coronagraph, which you can actually go see. It's in Moudon. Sorry? Moudon in France, outside Paris. Leo was a consummate instrumentalist, and he built that thing out of like pieces of wood that he had lying around the lab and lenses. But many coronagraphs, the ones you'll see here, are a combination. Some of them are external, and the ones in space tend to be externally occulted. The ones that are used on the ground tend to look closer to the disk, and so they need more precision than you can get with a pure external occulter. So you tend to use a low scattering optic, and then some way of rejecting the light from the disk itself. So those are internally occulted. Internal occultation doesn't get you very far out into the corona because the brightness gradients are steep, and there's a necessary first optic that does scatter some light. So for these broad field things, you really want an external occulter, which there's a whole field in how you design those to minimize the diffraction around. And then, you have to deeply baffle everything, and there's post-processing involved. But fundamentally, you're looking at the sun, you're just blocking it out.
Sorry.
Yeah, I have a question for David, actually. I remember in the beginning of your talk, you mentioned that the fact that the spacecraft is spinning can sometimes be used for your advantage. But I happen to know that even if you look at the quick looks of, for example, semi-spacecraft, you can often see either the spin tone or the integers of the spin tone in electric field and magnetic field. And it's, I guess, sometimes can be very unfortunate if you are interested in some waves in this frequency range. So my question is, how challenging is it to get the data cleaned from all the effects related to the spinning of the spacecraft?
Very challenging. So it's a lot like what Craig was talking about. You get these sort of known artifacts in your images, and then you can try to Fourier process them. But even if you do that, you're introducing other artifacts, or you're eliminating things you want to measure. And so again, it comes down to sort of philosophy. How much of that do you leave in and just know that it's there versus how much do you try to heavily process the data to remove it, but introduce other things? And with the spin tones in particular, you get weird stuff because the spin is not symmetric. For example, the 4 probes that you have in the electric field instrument for Themis, they go in and out of the shadow of the spacecraft. And when you go in and out of the shadow, it changes the coupling to the plasma. I was trying to think of a good analogy while I was, while everybody was asking questions, and I think I came up with one, trying to measure an electric field is like trying to measure the gradient on a trampoline while 10 people are jumping on it.
Yeah, yeah.
Everything is moving and you're trying to understand what the background baseline is. And when your spacecraft is spinning, now each piece of that is sampling a different part of that bouncing surface. So typically the best way is to know what you're looking for and to understand roughly what the spin tone artifacts will look like.
Thank you.
So I have this question that came to my mind before, but I'm curious about everybody's opinion. So for example, we have satellite missions that are clusters of spacecrafts. And you have instruments on each of these spacecrafts. And it happens that some of these instruments die. How do you deal with this missing data? Like, is there a way, because there is a reason there was for example, MMS, there is 4 spacecrafts, you're measuring something and you have one spacecraft that is offline. Is there a way to handle the missing information from, I don't know?
Sure. So this applies to any constellation. It applies to Punch just as well as it applies to MMS. Generally, you try to design things so that they, what's known as gracefully degrade. So if you lose one point of the measurement, you don't lose all science, you just lose a part of the science. And so every time you lose an instrument or a piece, you sort of degrade things, but you try to set your science goals such that they can be achieved even with some of the degradation. That's one strategy. Other strategies are just redundancy. MMS is one of the most redundant spacecraft, scientific spacecraft ever built. It has at least two of everything. And so when parts, we even had, for example, the signal processing board for the electric field instrument is redundant. There's a cold spare that lives on the spacecraft so that if one goes out, we swap it. But that's, billion-dollar-plus mission. So if you have the money, you make it redundant. If you don't have the money, you make it redundant by either putting up more spacecraft or setting your science goals so that degradation, you can live with the degradation.
I love that answer. There's another direction too, which is that the problem of what to do with a spacecraft after something breaks is different from the question of do you need that thing up front, right? Spacecraft and observatories and instruments are typically designed specifically to close a particular set of science questions. And the question of how do I build my thing to close some particular science is different than the question of what can I use this thing for now that it's in space, right? So an example of that is LASCO had 3 coronagraph channels, and it was there to close particular science connecting the surface of the sun out to the outer corona, and did so. But we lost C1, the inner coronagraph. It was lost in 1998, 2 years into the mission. But that doesn't mean that LASCO C3 is not useful, right? So it's just useful for different things than that particular science.
So you just mentioned that that MMS is it's redundant, and I am wondering if this redundancy is helpful to cross-check your data, because in information theory we have the algorithm that has to rely on the redundancy to make sure to prevent that data gets destroyed during the transmission.
So one of the problems of in situ data, which is what Craig mentioned, is that you measure a lot, but at one point. And so when you try to do things like cross-calibration across data sets, like let's say we're trying to get MMS and Themis to talk to each other, or measure similar plasma so that we can test whether the instruments see similar things or whatever. That depends on orbital dynamics and timing and luck. These missions are not coordinated, right? We try to coordinate them at the very highest level, right? And NASA attempts to make missions that are trying to measure the same thing at the same time, but really they're not, right? Because it comes down to congressional whims and funding and whatever. And so you often rely on times when you get lucky conjunctions between spacecraft to try to calibrate or cross-calibrate across missions. Missions that are constellations, you can get around that and you can cross-calibrate from spacecraft to spacecraft, like on MMS. Because they're so close together that sometimes, especially if you're measuring like an MHD quantity, you're pretty sure you're measuring the same thing with all 4. And then you can cross-calibrate. But generally, the missions are so sparse and they're measuring such different pieces of the plasma that cross-calibration is almost impossible many times. So what we do instead is we try to measure against sort of things that depend on fundamental constants. Like, for example, if you can measure the Langmuir line, the frequency at which plasmas resonate, that's good to fundamental constants and your ability to measure frequency. And so you can use that to get a total density, and then you use that to calibrate your particle instruments, and then you use that to get your spacecraft potential. So you can use different aspects of the instruments within an instrument suite, but generally, spacecraft to spacecraft, it's not very easy thing to do. Space is big, in situ measures a small space.